Alright, so today we're getting into forces, energy, and momentum. Of course, I break this unit 4 down into 3 different categories. The first one we will get into Newton's law, and the second one we will get into work and energy, and the last, impulse and momentum. This is just, we have 3 different ways to analyze the motion. Engineering, of course, in engineering there is um you know many ways. Now you don't have just one way to solve a problems, so you can use force method, you can use energy method, you can use momentum method to solve a problem in. So that's how we work, like we try different methods to solve the same thing, and of course we try to find the best method to do it. So smart engineer, we usually choose this the easiest one. And of course we have like a small inertia, it is going to have like a um just try to remember. Sorry, I went outside and come back. So anyway, so just remember like the mass matter. If you deal with the little mass, to stabilize the little mass, whether it's in motion or in a place in the space, you don't need a lot of stabilizing forces to do that. So that's what we're trying to show you. Of course, here is a little graph simulation. You can see the object that is at rest is going to stay at rest because of the law of inertia. The object that is going with a constant velocity without having an acceleration will go in that motion, until you disrupt that motion with external force. Because law of inertia, I do this again, or we can wait this advertisement from the YouTube because they give us a lot of space for us to use for the education. So anyway, it's just showing you with a little bit faster rate on it. Okay, then Newton's second law is different because we are especially studying or take a look at mass and acceleration, and of course here you have the acceleration, so therefore we already know acceleration depends on the velocity. We're looking at the rate of the velocity, changes. And do not forget that, so your force is equal to mass and then time the acceleration. And always remember, like your force will be always bigger than the magnitude. The force magnitude is going to be bigger than the acceleration. Amount is because we're getting the effects from the mass and the effects from the acceleration. So therefore you gotta put this amount of force to move the mass, with an acceleration. So that is more than taking a place in a space. That is more than moving with a constant velocity, because now we have a specific acceleration. So that's mentioned here right there. So therefore you're dealing with a force that can move the object, and of course it is increasing in speed. Acceleration means you're increasing the rate of velocity. So larger force, you're going to have larger acceleration because they are directly proportional to each other, and that's your algebra. Your larger mass is going to give you a smaller acceleration. So let me go and here of course you have your force and then an A, here like this. And of course we can make mass constant. So if you make the mass constant, force is directly proportional to acceleration. If we make, of course, the force constant, we can move in the algebra operation like this in mathematics. So here we can write it this way. So you can be able to make any variable constant. So here's, if you want, of course, this force is constant. What we have is your mass is going to be indirectly proportional to the acceleration. So if your acceleration is high, okay, it means you're dealing with a small mass. Okay. So that's what we're talking about here. Yeah, so if you have a smaller acceleration, then you will be dealing with the larger mass. Your zero force is zero acceleration, because if this is zero, your acceleration will definitely be zero. Your units for force is Newton, your unit for mass is kilogram, your unit for acceleration is meter per second square, and of course, SI unit. Then we get into the Newton's third law. Since I already gave you a lecture, this is going to be kind of like a review listening, okay? So we're going to go a little bit faster than getting into details like in the classroom. So forces, they don't cancel each other. You know, they act on separate objects. Of course, they will cancel only if the amount of that force equal and in opposite direction, because forces are vectors. You know, don't forget that. And of course, they act, this object is going to act on that, and that object is going to act on this. Here we're just showing an example of gigantic objects like your Earth and then your Moon right there. So this sometimes explains require pushing, okay, gripping, because the object, they act on each other. So that's your Newton's third law, meaning there is an action and reaction. For every action, there is an equal and opposite reaction. So if you apply that to every single little particle in the air, every single touch point on the surface of your ground, okay, every little touch point between any two objects, and that's a lot of complexity in the world that we are in. So forces, make sure it comes in pairs. There are layers that we're thinking about, the particles, little things, objects, the medium things, and the big bodies, okay, giant things, all in the universe. So anyway, so these forces come in pairs and they act on different bodies. Walking, of course, so your example, rocket propulsion, another example, okay? And of course, here is another example with a little, tractor. And then, of course, so here is a little cart, your trailer behind it. And of course, so this is acting force on here, and that is acting force on here. Yeah. So the car is acting the force on the car, and then the car, in this case, the tractor is acting the force on this little car, the trailer. Okay. So anyway, these are just exaggerated drawing cartoons. Okay, drawing showing you big. But with engineering mindset, you have to go into details in your mind. You have to use your mind to be able to see and picture what's going on, the whole thing, everything. Okay, it doesn't say only the big object or the medium object or just a mechanic. Plus, the law is, okay, applying everything that we know in this world. That's why the laws are scientific laws are very powerful, okay? So don't take it for granted. Okay, now we see a little bit of the animation right there. And this is just showing you for every force of action, there is an equal and opposite reaction. Your Newton's third law formal definition, of course, the Earth is going to pull the moon with the same size force that the moon is going to pull the Earth. And that's why the Earth is at that position in the solar system, and then the moon is in that position in the solar system, okay? And remember, our solar system is will not be staying in that stability forever. Okay, so it can, since everything is in a constant, right, nearly constant motion, and it is of course happening in a very huge space. That's why it looks like stable. Of course, for human years, that's a lot, millions. So for star years, is nothing. It's just a blink of a second for them. So anyway, just try to remember where you are, the region, time going with the zones measurements. So what measurements are we in? And of course, your measurement is not the same as from the point of other location in the universe and how they measure it. Okay, sometimes I have to take a break to rest my throat. Okay, we've been talking all the time, prepare lectures, talk in the classroom, talk over here, making videos for you guys. Okay, because the student can't be able to come to class sometimes, so they depend on the lectures videos. Okay, so here we go. So Newton's third law, and of course we're going to give it a little time to for this thing to go away. Some of the advertisement seems to be okay. I learned a lot, like many different things that I don't even know. It was good. So anyway, so here's a block showing you the action and reaction. Okay, so it's a totally very common diagram with a block showing you two different direction of the force, and here is your surface acting on it, and here is the block acting down. Of course, every time we study, we try to ignore all the environmental forces, but in calculus we don't ignore all the environmental forces anymore. We actually take that into account. Okay, so it depends on the level of study as well, where you don't have to do all the time. But in a very beginning, level 1 or level 0, you are going to ignore everything. So that's why we usually draw like this in a very, very simple way to showing the action and reaction. Newton's third law, the block on the table. And I think you can see this in many different, of course, textbook. And people who try to get into a complex textbook, just make sure you read and understand what level you are in. It depends on the level, the calculus. Okay, they're different. Okay, then free body diagrams looks like this. And do not forget, these forces are resultant. Okay, they're not just a single force acting on it. You have this determined by the environmental forces altogether combined. Okay, so when we write here as N, that's a normal force, and that's, I say, every touch point between the block and the surface that it is sliding. Okay, and of course, also this friction is going to represent all of the friction combined, okay, contributing to it. I wouldn't say combined, contributing to it, the final, resultant one. And then of course, then here is your force. So before solving a problem in dynamics, so we always draw a free body diagram like this. Abbreviation, we call it FBD. And here, of course, you can see we usually show the weight, the normal force, the applied force, and then, of course, the friction. And this force is the resultant. So you can break it down into two. And one is here in this line, x, axis, and then the other one is a y. So on x-axis you have a f, and then cosine. Cosine just telling you that I am on a direction, and that is the x direction. Okay, it means that I am a contributing force, not a contributing component force, and not the resultant. And here another component force contributing to this final resultant force. So that situated on along the y-axis. Why does it have to be x-axis? Why does it have to be y? Because we made up that way according to the coordinate system. Okay, so make sure you understand that. Of course, you have opposing friction force. That is opposing this resultant force F. But the resultant force win because there is motion going down that slope. Then you also have this another your weight, which is this mg, your mass and acceleration due to gravity is going to give you the weight of this little block right there. Also, this is a resultant force, so therefore we can break it down into two components. And for the weight, we go opposite of your force. Okay, so this is going to be the sine, and that is going to be the cosine. Okay, so be very, very careful. That's just a Pythagoras theorems. So you have to go back to geometry to review that. Okay, so if you skip, you usually love to skip the free body diagram. Okay, make sure don't skip it. All of the good students, they always draw this. Okay, the more you draw, the more you get this picture by heart in your mind, and you don't even have to draw it anymore. You totally get it. So this step is really, really good. So people like me who have a photographic memory, we can remember this. Okay, so like we can read the books and that just in our head. But people who don't have the photographic memory, you've got to practice, repeat. Okay, the more you repeat, your brain is going to automatically get it. Okay, all right. And then of course a free body diagram animation is showing you how to do it. Okay, how to draw. So you're going to start with your axis. and then of course you're gonna do your normal force, and then your resultant of the external force applied to it, your friction, yeah, got to be in your free body diagram along with the weight. Okay. All right, then your example is a horizontal force. Example here, 10 kilogram box, 15 Newton force. We don't have friction, we ignore it. It is a frictionless. So you have your acceleration, and we, of course, this can come from your F is equal to ma, so don't forget that. Okay, so therefore your acceleration is F divided by m. See, so F divided by m, so that's just your algebra. Okay, we're just switching the side, pushing all the F and m on the one side, and then of course leaving this acceleration on the other side, so you can cleanly calculate this. Okay, so that's a 50 for the force, 10 for the mass, and of course you calculate it and you will get the 5 meter per second square. Make sure you understand your unit system. I don't want to go over there again. That should be in your 135. Okay, measurement conversion. You have to convert from one unit to the another, and we have a three major unit system. U.S. customary. Thus, I think they're changing the name to American units, and then of course the next one is taking everything American. Anyways, the American units, and then the other one is your SI units, and then of course, and then your metric. Okay, do not confuse between the SI and metric. So make sure you review your 135 in unit conversion and the unit system, and of course, it is always good to draw your free body diagram. Your example is your inclined plane is right here. Another one, and you have a 20 kilogram block, 30-degree incline, no friction, and your force is has like a drop, going down slope. Okay, so which is a slope like this, and then your force is like that, and you have your mass, your acceleration due to gravity, and then of course so we know that sine theta is going to be on your y-axis. Yeah, so here bring back that. So therefore we plug it in all the numbers, and you got 20 for your mass and 9.8 for your acceleration due to gravity. And then of course your sine, okay, 30 is going to give you 0.5. Use your TI-89 or EXA calculator, or you can AI it. It's going to give you 98, okay, Newton. So your A is equal to 98 divided by 20, and you're going to get 4.9 meter per second square. Okay, your work. Your work is nothing but this. Okay, so you have a force. We use a force to push a block, and that block is going to take a distance d. And the force that required to push is this guy. The distance that this block takes is going to be d. It means that your block has work, okay, from here to there by moving itself from there to there by using that force. So you get work is, okay, how much force did you use to go, all right, to push an object to that distance is your work, okay? So the amount of energy transferred by a force acting through a distance is your formal definition. Pay attention to all of the operation in math. Every time you have a multiplication, your end, okay, magnitude of your work here, okay, in this case, is going to be bigger than each one of them. So the work got to be bigger than the force and got to be bigger than the distance magnitude. Yeah, we're looking at the value. Magnitude means we're looking at the values only. Why? Because work is influenced by two variables. Yeah, so therefore it is its magnitude will be greater than each one of these magnitude. Your work requires the motion. Without the motion, this thing will never move from here to there. Yeah, it means that it moves from here to here that amount of distance with this force, and of course you work that distance. So that's how we say it on the side. Yeah, and of course the unit of your work is going to be joules, and we use the J, a big letter J. Your unit is going to be force is Newton, your distance is meter, so therefore you have, yeah, Newton meter. Right now we're just gauging with one, meaning like in 1 joules we have a 1 Newton mass, 1 Newton force. Okay, it's going to move it's going to move the block 1 meter. Okay. All right, the next one is energy. So we get into the energy. We have two different types of energy. One is the energy that needs to take a position in the space, and the other one is energy that needs to move. Okay, itself or it moves or something else. So energy is again is ability to do something. So it's a capacity to do work. So the energy of motion again is okay. We call it in a technical term kinetic energy. Yeah. So this is a mechanical dynamic term. Kinetic meaning I this energy I use it to move. Okay. We are going to bring back a block on a table example again. Okay, and of course, do not forget the mathematics. Okay, and here will our influence. Okay, our influence from the velocity is a squared effect. So this means that we have a square effect, meaning like this kinetic energy is bigger, yeah, than this square. Of course, we also have an environmental factor. Okay, we compensate in that factor calculated, and it happened to be about 0.5. I said about, okay, it's not absolutely 1/2. There's no absolute things in the world. It's always an estimate, okay? Very, very good estimate. Of course, your velocity doubles, meaning your kinetic energy, okay, is going to go quadruple. Yeah, so the KE is going to get quadruple effect if you're going to double your velocity because we are getting the square effect. So if V is 2 times, so you're going to get 4, okay? 4 of this whole thing. Why that is happening is going to be, of course, here, let me just go ahead and show that, okay, your kinetic energy is equal to your environmental adjustment factor 1/2, and then you're looking at mass going with a velocity, but then on this amount, okay, after doing many experiments, we have determined we're getting the square effect. Okay, so the velocity got to be squared. All right, so now what we want to show you is this. So when you have a double, yeah, so double velocity like that, we are going to square it here. Of course, the rest of them stay the same. Okay. So therefore this is actually 4. Okay, so you're gonna have like 4. All right, and we want to show you that. Okay, so if you have like a double, sorry, I forgot to be here, so double velocity, and you are going to get that. Okay, so meaning like your kinetic energy grew quadruple. Okay, it grows quadruple. So anyway, so that's what it is saying. Do not do, okay, like I almost did. Do not do the V is 2. It doesn't say velocity is 2, okay, meter per second squared. It said your velocity doubles, yeah? So therefore, you're going to have to do double. So therefore, you get kinetic energy quadrupled. Why? Because of the squared effect, okay? All right, now we're going to look at the visualization for your KE variables in the mathematics relationship here. Let's skip this. Okay, so we have a block here, and then of course we're looking at the kinetic energy versus velocity. So your KE here, velocity, it means that your when you of course increase your velocity, you can see your kinetic energy is going to go up. Okay, when you increase the mass, you can also see the kinetic energy is going to go up. So this simulation is just showing you the direct proportional relationship between the kinetic energy, the mass kinetic energy, and the velocity. So we get a little exponential graph because of the square on the V. Your graph is not straight line, it's going to be a curve. And of course, your data go up. It means that if you change the mass to increase, if you change the velocity to increase, you're going to get kinetic energy, okay, grows that way. Yeah? So meaning like you will need more energy, yeah, if you have like a bigger mass for it to move. Yeah, so that's what we're looking at. Then we will get into potential energy. Okay, so your potential energy, we usually look at the height. Yeah, so for potential energy, we want to make sure where our things are in this environment, okay, at what height. And depends on the height, you're gonna have to use a force to keep that okay object in that position. So if you look at the balls here, we can see, okay, like from here to here is a 5 units height, and that is like a 10 units height. So in order for the environment to, like hold this thing right there, you got to put that amount of energy by the environment to hold the ball, okay, at that position. Of course, a lot of the textbook would trick you and tell you it needs this amount of energy. Like it usually former professor, long time ago professor, like to reverse it to trick you. So you need the teachers, to be able to understand that. Right now, you have to work very, very hard and also use AI, everything, okay, that is available for you to understand this knowledge in a short amount of time. Okay, that's your goal. Why? Because our environment isn't stable. Okay, our planet isn't stable, and that it's every university is starting to tell you about it, so we can enhance okay our understanding of the very very huge universe. So make sure that you understand, okay, what you're doing. So you need the environmental forces that amount to hold this thing at that height. Okay, for this you have only 5, so you need about this height because your height is changing. The smaller the h is, your potential energy, to keep that position is smaller. The higher the height, you gotta put more energy to hold okay this mass at that height. Why? Because you have to work against that acceleration due to gravity. Okay, because your body is pulled by the gravitational force. So therefore, you have like something like this. Of course, it's always pulled by the gravitational force like this. Okay, this is a force. Don't forget, F is ma. Okay, so therefore we write here your acceleration due to gravity. So it becomes that's we're talking about the force. So in order for you to compensate that force, okay, we're gonna have to use that amount of energy. Okay, so we just go with potential energy. I am writing the conventional symbol. Of course, there are many books who is going to use different that is going to use a different symbol, but it's the same thing. MGH, okay, and this, okay, need to be compensated by this height by applying, okay, this amount of energy. Okay, then we are going to get into this a little animation, so you can be able to see PE is equal to MGH. It is going to show you the increasing height is going to increase the stored energy, and do not get yourself tricked, okay, with the stored energy. It means that the environmental forces need to stabilize, okay, that object with that amount of energy. Okay, so of course the object also have to give the same amount of energy back, okay, so it will not be able to get out of that position it is taking. Either in a shorter height or a long or taller height. So increasing the mass in this video showing you increasing the mass is going to increase the stored energy. Potential energy is going to grow, okay, linearly with the height. So right now we're not having a squared in our equation, so therefore your graph, okay, is not a curve, it is a straight line, and it's still showing you the directly proportional, the relationship. So we are going to, of course, go back, to this, and here your PE, okay, is directly proportional to H. Your PE, okay, is directly proportional to M. If G is always constant anyway, because that's around 10 meter per second, okay, for the gravitation due to, acceleration due to gravity. And then of course your mass, we can also make it a constant, yes. So here your mass in G is constant, and here your G and height is constant, so therefore you see they're directly proportional. So if you increase the mass, you're gonna have to have a potential energy increase, for for this to stay in the position. Do not forget you have a weight and then you have a lifting force. Okay, two things going on for something to stay in the position. Don't just give me one. All right, do not forget this force, and we call that the PE. Yeah, and this force is this guy right there. Okay, and that's another way that we write. Okay, FH. So anyway, so you've got to put equal amount of force, okay, to that to make sure that it is staying in that position in the space, okay, at that height. All right, then we're gonna come back here into the to the juggler here. So your work energy principle. So here we're looking at the work and we're looking at the kinetic energy, and we come to know you have work done if you look at the kinetic energy before and kinetic energy after. It is going to show you, yeah. So and we call this a work energy principle, because there's a balance between the work and kinetic energy. Balance meaning like they compensate each other. Okay, they compensate each other. So here, of course, you have kinetic energy in the ball because you are juggling, and then when this ball, change the height here all the way to the higher height, you do have, you do have another energy, which is your potential energy. So you're seeing kinetic energy represented by little capital T, and then of course your potential energy represented by capital V here. So it means that the total sum, okay, which is the sum of the kinetic energy and the potential energy before is equal to the kinetic energy and potential energy after. It just changed the position, for from here all the way to here. So it got to move and then take that position. Okay. So anyway, so and don't forget, we can be able to write it this way. So work equal to change in kinetic energy, like that. However, we also make sure that some of the work are conserved, position, initial, and then of course the final work. We can be able to know that each system has a kinetic energy and potential energy combined. Okay, sometimes this is zero and you only have a motion. Sometimes that's zero and you only have a stable or static position there. And sometimes you're in between, like your juggler right here. Okay, it means that it takes a position and then move, take another position and then move back. So you can see the swing, right here. And then of course we're gonna separate it into initial, and then the final, like that. In some textbook use the kinetic energy as T, and some textbook use a potential energy as V. Now we're writing the situation before and after with 1 and 2, So anyways, that's what you need to understand about the work energy, balance. It means that we're balanced. It's just like things take position, things move position in the space, and when they move, we gauge the how much motion and how much stability or static motion here, dynamic and static. Sometimes we call that. How much energy you use to move and how much energy you use to stay or take a position in that space. And of course, the energy cannot be destroyed. You can only change the form of the energy, meaning from move energy to stay energy. You can change that. Of course, if you have 100, then it can go like 70 here and 30 here, and then here like you get by like 20 here and 80 here, kind of like that. But in total, it will always be 100. So that's what we call that the work energy principle. And do not forget, Ke can also be written as a 1 by 2 mv squared. And so if we want to make the complex equation, and this of course can be written as 1 by 2 and then m, and b squared. suppose you don't have potential energy, so it will become zero. Yeah. So, and that is what we're talking about when we think about the work. Okay. So of course, we're looking at the change. Yeah. So don't forget the change. So it can be able to study in calculus with the uh, function of time. Okay. So we're looking at something changes along the timeline. So when the functional time come in, then you have a little bit issue to calculate, but it's the same thing. But I want you to start from the very basic. Okay, do not skip your basic. You have to start from the very basic, and your basic is this before you ever go into a complex one. If you skip the basic, you want to be sorry. Okay, so if you do not skip the basic and you are master of the foundations, okay, material, everything is so easy. Okay, so instead of solving for time and acceleration, make sure you compare before and after. This every time you see a little delta, we're dealing with a chain. Every time you deal with a chain, you have a before and after situations. Okay, and you subtract before from the after, because after usually is bigger in amount than before. Okay, so therefore you can be able to do the work energy, okay, balance by calculating like that. And here we have another graph, okay, showing you the work energy principle. And of course, understand that your work is a change in kinetic, okay, energy. And of course, it's showing you how we apply the force, over a distance. Is working here in this diagram. So we can see the work changes the kinetic energy starting from the rest. It's going to lead to work, okay, which is kinetic energy can also be written as 1 by 2 mv squared. And of course, your friction sometimes affects the energy transfer because it's opposing the direction of the motion. So here we're showing like how we change the mass, how we change the applied force, how we change the friction, and you can be able to say the velocity. Here is your work and kinetic energy and the time, velocity, and the time. You can see as velocity increases with time, your energy also go up. Your energy has a square effect, so therefore it has a curved line. Your velocity, we're looking at the distance per time, so therefore it is a straight line. Okay, so we can look at the numbers. C, your work and kinetic energy is the same amount. And that is a proof of W is equal to delta KE. Okay, so then we are going to get back into our basic work on a box example. So you have a 10 kilogram mass and you have a 20 Newton force and you went like 5 meter this block. Okay, so you have 100 joules for work because we use force, which is 20, and then distance is 5. So we use the F times, okay, we use this. So I'm just going to write it down here. Force, yes. So this is what we're showing you. And then, of course, your distance, So therefore, you're going to get your work, okay. And then use that work in here equal to your kinetic energy, which is 1 by 2, 10 v squared. It's going to give you your velocity. Make sure you get the square rooted, okay. I can make this way. It's easier for me to draw. Alright, so here first we are going to of course put the velocity square on this side, 2 times 100. We're doing our algebra right here. First we move this thing to that side, okay, and then we're going to move that thing to this side, okay. And then of course if you want the v, all you have to do is to square root it, the whole thing, yes. So we go like that. I'm just going to show you step by step, okay. So that's how you are going to solve it like this, and you are going to end it up getting this, okay. Use your TI-89, your calculus calculator, and then you will get that, okay. Alright, and I want you to show the step like that and you do it, okay. Even though we allow you to use the AI, make sure you still understand what you're doing. Otherwise, there's no use, okay. There won't be anything in your head. you will become the master of cheating. Okay, so make sure at least do your work or understand. Okay, AI should be used only to enhance the efficiency in your learning. You can use it as your assistant, however, to cut your time. Okay? However, you still need to understand what's going on. Okay. Otherwise, you'll get into trouble, or you will never get a job. Or even though you get a job, you become a faker, and you will come back out of it when you can't do it. Okay, so linear momentum. So we'll get into linear momentum. We write it this way, and this is your rule. And the formula is like this. Okay, we're looking at the mass, which is an object, going with a velocity. So now in momentum, we're studying, okay, how big of an object, okay, is moving how fast. So that is called the momentum. So the force of movement. So that's the formal definition. Linear momentum. We're still in linear. And of course, we always study from the linear, your one dimension, yeah, before we ever get into two dimension and three dimensions. So linear momentum is the product between an object's mass and velocity. Your unit mass is kilogram, velocity is meter per second. So therefore, your momentum is a vector. Heavy and slow, that's what we're looking at. Okay, heavy, slow. Your mass is heavy, your velocity is slow. Light and fast, your mass is light, and then of course your velocity is fast. Okay, sometimes they can be matched because the momentum can be conserved. Okay, all right, then we will take a look at this, of course, a moving block. Okay, so here you're going to be able to see a live graph of momentum versus velocity. And here we have momentum on the y-axis and velocity on the x-axis. They are linear, so therefore we get a straight line. They are directly proportional to each other, so therefore you're going to have a straight line and going up on a forward slope. Okay, so going there, go all the way up, and of course physically your block is moving. Okay, we can go down and we can go up. Okay, we're just changing the mass, and you can see your momentum. Okay, go up. If we change the velocity again, your momentum go up. So therefore we can be able to understand, okay, how your momentum is your rho, mass, and then velocity. If we make the mass constant, your momentum is directly proportional to the velocity. If we make the velocity constant, your momentum is directly proportional to the mass. If the mass increase, your momentum increase. If the velocity increase, your momentum increase. And that's what this, okay, simulation for this block, okay, is showing you in that graph. It just is showing you the momentum versus velocity relationship, and they are again directly proportional. Mass and velocity are directly proportional to your momentum. Okay, so never forget that. All right, and then of course, we are going to go to the next one is impulse. Your impulse is J, and we're looking at the force this time. Our momentum, where we were looking at the mass with the velocity, how heavy. So here we're looking at the force, okay, and how long we apply the force and how much force we apply is your impulse. Yes, so impulse is accumulated effect of the forces acting over time. So now the time factor come in over time, so therefore you see a little delta right there. Yeah, change in time, the time that you started, and then of course here is your impulse. We're looking at how big the force is and how long we apply the force. Okay, the force is always with delta. This guy is delta, showing you this. So meaning you have a time period is right in there. Okay, this amount of time, and you apply that amount of force, and you will end up getting that amount of impulse. And again, you're dealing with the multiplication mathematical operation, showing you your impulse will always be bigger than this or that. Okay. All right, your unit is going to be Newton for the force and the second for your time. Of course, we can also bring this, okay, on this side. And then, of course, we can be able to say, all right, this impulse is actually the change in momentum. Yeah, so here, the change in momentum, like this, okay? And of course, the change in momentum meaning like this. You have a two situation, okay, going on. So let me go back here. And then thus, delta mean you're dealing with the final situation minus the initial situation, yeah, which is, and I am writing it in mass and velocity, okay? And then here, mass and velocity. I made a mistake here actually. This is supposed to be 2. It's so hard to draw with this little cursor. And then of course, so this is initial, and thus your final. Then you will get your impulse. Impulse is a change in momentum. Momentum is the force times a delta t. So therefore, yeah, the force times delta t. Okay, let me move it to this side. Let me expand it. So therefore, yeah, your force times delta t is equal to the change in momentum. Okay, and then of course you can put the whole thing right there. It's the same. Okay, so your unit Newton time is S. We can write it this way because that's the impulse and that's the impulse. Just a different way of showing, yeah, different symbols. Okay, then we will get into how much force changes over time. So how impulse is calculated. Okay, all right. So and here it's a little bit complicated graph in simulation, and this is what we use all the time for us to be able to study many different kinds of variables and factors here. So here we are, of course, playing with the mass, yeah, and then the distance, and then of course momentum, yeah, here, and we're drawing your force, okay, and then of course your momentum, and then this block is going to go up. So your impulse and the change in momentum, they equal each other, you know, and they don't change. In calculus, of course, we write it this way because we're getting into the integration to look at either area or the volume. Okay, so this is just telling you, hey, we're like moving away from the one-dimensional calculation. We're getting into some form of x and y, yeah, dimensions or 2 dimensions. We have to go with calculus. Of course, here we just simply say, okay, delta p is equal to j, which is change in momentum is your impulse. Okay, and do not forget that. Showing you the current time, and then of course it's showing you the current force, and then your impulse, okay, calculated to be this amount. And then we also look at the momentum, yeah, and momentum we calculated this way, and we get about this much, okay, 20.79 meter per second square. Okay, so impulse momentum principle. I'm trying to drink some water. One moment. All right, impulse momentum principle is just like your work energy. Yeah, your impulse is equal to the change in momentum, and I have already calculated that for you. Yes, and show you like how we ended up like this in the other equation here. This one, okay. So how we calculate their just the impulse equation written in 2 different ways in terms of force and time, and then in terms of momentum. So the impulse of all the resultant forces acting on a particle is equivalent to a particle's change in linear momentum. So we use for short, fast events, so bat hitting the ball, car crash, robot grippers are all of the example that you can be able to picture in your mind. Okay, I will try to animate it for you when I have time. Okay, it's just like we don't have time to create all the animations. Yeah. All right, so we don't need a detailed force curve here. Just the total impulse is what we're looking for, and it is really, really, of course, a powerful equation because we can be able to see the impulse amount. They don't really change. Okay. So what can we do with this? We can be able to calculate the velocity, mass. We can be able to calculate the time or the force, yeah, from this equation. So algebra is really powerful because we can do these things. All right, example for impulse, we have a 0.2 kilogram ball, and then of course that's your mass 10 Newton force, we apply 0.1 second. So now we can get the impulse. So since the impulse is equal to the change in momentum, yes, and here you have only one situation. We have your first situation is at rest, okay, which is this guy. Row 1 is starts from the rest, so this is completely zero, okay, so therefore we can immediately write, okay, just one like that. Of course your mass is 0.2 kilogram because this ball weighs that much, and then of course your velocity is the one we want to calculate, so we are going to divide 1 divided by 0.2. So in this example what we do is we divide 1 with 0.2, okay, like this, so you will get 5, of course, a meter per second. Of course, there was a student asking how to do that. These are pretty easy ones. You can either Excel it or AI it or whatever you want. And this 0.2 is 1 by 5. Yeah, so when you flip it, 5 come up like this. And then leaving, of course, 1 by 1. Yeah, this, we can move this to the above that bar for the division bar. Okay, so that's just algebra. So you enter the 1 divided by 1 cancel out. So you're left with this. So make sure you review your mathematics. Because they're too simple, so we can do it, you know, in the head or in the math lab or your computation software, you know, anything you want to use. Here is a simulation of a force, yeah, showing you with a particular duration, your time, and then of course your impulse is calculated. Yeah, so your force time t is what we're doing here, and of course we write it down. When you have time, and you can go with a slow motion here, or just pause it and drag it, and you can be able to read it. You know, we can make it bigger. I already show you how to do it over there on the YouTube site, or you can just make it here big. Okay. I'm not going to go over this again because I already explained that in our classroom. Yeah, just make sure that we are just looking at, okay, your force with the time, yeah, which is like this, of course. And then of course we understand that they are directly, yeah, proportional to each other. And that is a simulation for the impulse accumulation here. So we're calculating impulse from force and change in time. Okay. All right. Then we will get into conservation of momentum. So if no external force, if you don't have an external force, your momentum will be conserved, and we write that way. So initial will equal to final if you don't have an external force, you know, to disturb that equilibrium. So your mv1 is equal to mv2, and of course this is a sum, always a sum, because nothing is simple like this in the real world. Yeah, so therefore you're gonna have like an m, and then 1 2, of course a v 1 2, and then minus the sum of m, okay, 1 2, and then v 1 2. Okay, so it's just showing I mean like, hey, I am a series. Yeah, I go from a point 1 all the way to the anywhere to something. So that's what we're talking about. It's just you're looking at the change in momentum. Yeah, here of course we come into a series of m. Why? Because there are a lot of them, by the way. It doesn't really matter what that is. If you do not have an external force, you're going to end up getting 0, yeah, for any kind of a system that you are studying. So if the result force on a system of particles is 0 during an interval of time, your linear momentum must remain constant. So that applies to your collisions, explosion, your objects sticking together. Example here, your momentum between the state 2 and then 3 is completely conserved. Okay. So there was a student who was asking me about this. Okay, it is just don't go into the picture and try to think was so hard. Okay, it was just saying like we do not have an external force, so therefore the momentum here, okay, will be just the same. That's what it say. It doesn't say it doesn't move. It moves. It moves with a with a certain velocity that completely conserve the momentum. Okay. All right. Example is inelastic. Inelastic means they will stick together when they collide. So that type of collision we're looking at. So you have a cart A and cart B. you're going with a velocity 2 meter per second for cart A, and you have to find the velocity of cart, okay, B. And of course, you have a 2 meter per, 2 meter for two, sorry, two, okay, for mass is second mass, and then one for the first mass. So here we write the 1 kilogram cart. The first mass is 1, and second mass is 2. And then of course, the second one is at rest, so your velocity starts with 0, and your initial velocity starts with 0. Your initial velocity for the cart 1 or cart A is going to start with 2 meter per second. Your initial momentum is going to be 2, yeah, because velocity times your mass is going to give you the momentum. Of course, we only have momentum for the first A, not the B, because B is 0, so therefore that's a completely 0. And do not forget your momentum is, your situation is like this. So let me write that for you here so you kind of get it. So you have one thing coming in with a velocity, and you have another thing, okay, with 0 velocity, and then they collide and go together, yeah? So that's what we're looking at. So initially, you have this, okay, and you have that. Since this B is 0, the whole thing is 0, so we don't have to worry about it. And here your mass is 1, and then here your velocity is 2, so therefore your momentum is 2, okay? So that's what it is telling you about. And after a collision, you collide and then you stick together because it is inelastic collision, okay? So therefore, we're gonna have another one like this again, yeah? So your M and then of course V, your mass is fused together. So you have 1 and 2. Why? Because this is 1 and this is 2, okay? So you have altogether 3 right here. And then of course, we do have to find this, of course, velocity, final velocity. And we already know this is a second, yeah, momentum. And then this is a first momentum, they conserve. So therefore it is equal to 2, which is your first momentum. So now you have this, okay? So your 2 is here, and then that's your 3. And you will be getting about 0.67, yeah, meter per second. So anyway, so that's how you calculate. And of course, so when you calculate, make sure you do this, okay? And I really want you to do calculation that way. Make sure you draw diagrams. It helps you a lot. Okay, diagrams are very good for visualization to understand what's going on in that problem or situation. Okay. And of course, you can apply this to many different real-world situations. Your detective, your collision investigator, your insurance verification agent, you know, things like that, yada yada. Okay, so anyways, and then we go here, and we will take a look at the conservation of momentum simulation right there. And we are going to show the 3 cases of the collision before and after collision in this simulation. Okay. I am going to go ahead and skip this little one. And of course, you have your card 1 and card 2, and we play with the variables in that equation. Your mass velocity, and we have a velocity 1 and 2, of course. You have an initial position of this, and then of course, when you collide, when you simulate it here, they collide, and then it's going to change into a new velocity, and then of course, on both of that objects. Yeah, we have 2 objects going on, and then of course we try to calculate your P1, P2, and then the total. Okay, like this. We also understand that the momentum. Okay, you have 2 different types of collision: elastic and inelastic. Inelastic will stick together, and elastic they bounce off or go somewhere else. Yeah. And this simulation is showing you many different conditions here. So make sure you view this at your house and study, okay, with it, so you can visualize it, okay. If you don't study, all right, I don't know what else I can say either. If you don't study, you will not get it. All right, simple as that. You cannot get it by asking questions from other people. That's just talking, and probably you will get 1 or 2 points, but not the whole thing. In order for you to get something, you really, really have to sit down and study. Yeah, and a lot of the students, about 80%, just want to pass, and they want to pass without studying. So this is wrong. Okay, so make sure you read the book, study the handouts, study the calculation, and do not skip the basic. Make sure you master all the basic before we move into the second level. Okay, so here anyways I have demonstrated and demo the conservation of momentum with your 1D, meaning like we're just looking at linear, yeah, collision. And then of course we go into summary of this unit 4. Is it unit 4 or 3? Anyway, so this is the fourth energy momentum unit. And of course we have a Newton's law, force method, work energy, energy method, your impulse momentum. You have a collision method. So all these methods are applied. And in colleges and university, what we teach you is not the content. We're teaching you with the method. We use a variable. The meaning is in the word. Variable meaning can be anything. If you get the formula, if you get the diagram, if you get the method, you can apply it to various real world situation. Yeah, you ask for the real world. It's because you don't know how to apply these methods to the real world situation. This is the reason why student asking real world problem. But as a student, you're supposed to be studying in your mind and apply it. Okay, apply these methods onto the real world situation. And the more you can do that, the brilliant you become. The more you don't do anything, I don't know, the more you will be writing on everything. Okay. All right. So anyway, so this is your end of the chapter. And here is a source. I have to identify the source. Okay. And here engineer choose the simplest path. Why? Because we want to be very efficient. Yeah. So smart people always thinking about how to cut time. And here in college, we're teaching you that. So do not disgrace the professor by saying things that are not true to them. I gotta fight all the time. Hey, we're not doing like that. Just because one professor isn't smart, just because one professor is lazy, that doesn't mean you have to insult the entire population of professors. We don't deserve it.